third group of the afternoon. This is group 4. They've been working on what's called the therapeutic wheelchair project under sponsorship of McMain's Children's Development Center in Baton Rouge, and they'll tell you about their project and its results.
Hello everyone, we're group 4. We're doing a therapeutic wheelchair. My name is Justin Blanchard. With me today is Adam Blessing, Arthur Hebert, and Will Wascom. Our advisors are Dr. Jack Helms and Captain Dave Giornachano. For an overview, what we're going to be covering today, we're going to mention our sponsor, some backgrounds. We'll also cover the problem statement, our solution. Then we'll go through design revisions that we've made since we've last seen you all. Go through manufacturing, how we actually built it, testing, a budget of all our expenses, and then we'll wrap it up with a summary and then our sponsor slides show who helped with everything. Our sponsor is McMain's Children's Development Center. They've been working with the Baton Rouge community since 1954. They were originally named Cerebral Palsy Association of Greater Baton Rouge Incorporated, but they've since been changed and named after Dr. Fred McMain. He's been working with Dr. Frank McMain, excuse me. He's been volunteering for 33 years for his orthopedic service to Baton Rouge to help children. This is a little background on cerebral palsy. Cerebral palsy is a neurological disorder that affects parts of the brain that control movement. It typically occurs between infancy and age of 3 is when you start seeing the symptoms. It causes muscle tension and inhibits them from really participating in everyday activities. The children with this tend to cross their knees or maybe put them to the side and have like an asymmetrical figure, which causes the torso to turn so they can't really sit upright, and it affects the posture. These are some pictures of different posture at different angles. The first picture is of someone sitting in a conventional chair at 90 degrees. As you can see, the top, it tends to tilt forward, which is obviously bad for you. And then the second slide, the second picture is a little bit worse of someone sitting up and then leaning forward. The middle picture of someone standing up, which is a lot better than sitting down, but as you can see, it still has, a little bit lean to the front. The next picture is someone sitting on a saddle, just in general. As you can see, the top has a better posture, and the backbone right above the hips is brought forward. But when they lean forward, it has the best posture where it comes and curves but then goes up. It doesn't have a jerk to go straight up. So the last posture is what we've been aiming for our project. The problem we have heard is that conventional wheelchairs are not adequately designed for children with active participation in everyday activities. They tend to slouch back the occupant so they can't really reach forward and really work at a table or a computer or such. So that's the problem we're addressing. We had a solution of a saddle-shaped wheelchair which adjusts their posture. It also has a tilt feature so they can really lean forward with a chest support to keep them from falling out, as well as a seat belt. It has a height adjustment to accommodate for different size tables. It also has modular supports. So a chest plate, which we'll cover later in the slide, that comes out so you can easily seat the child into the chair. It has adjustments for the foot supports to accommodate children of different age for different size shins. And it's mostly designed for therapeutic care. It's not designed for transportation. Here are some functional requirements. Our sponsor mainly came to us with the project and said we want a saddle-shaped wheelchair that spreads the hips and allows someone with a bad posture to really be corrected. It also has a height adjustment and a tilt function, which are the main requirements they wanted. That's what they proposed to us. Restrictions that we found in certain regulations that it has to withstand a 150-pound load, and it's from ages 8 to 12. We need minimum maintenance so that the folks at McMain's don't have to really fool with it a lot, greasing a chain or such to make sure that it's really easy to use and will last for a while. We want easy modifications, as I mentioned earlier, for the foot supports. That way they don't have to really work too hard to do the adjustments. A few tweaks and you'll adjust it for the right size and that'll be easy. We also have modular supports for the chest support so you can easily get the child into the chair. Here are some constraints we had to satisfy. The FDA regulations stipulated that we had to do a certain angle to make sure the chair didn't tip over, which is obviously one of the most important things as far as safety. We also had to fit through a standard size door, which is 32 inches long, wide, to make sure that it goes through. All the doors at McMain's are over this dimension, so we're all good on there. We also wanted that the base length to not exceed 36 inches to kind of help mobility when you're going down a hall or such, to make sure you don't run into the sides. We also had to satisfy ISO's, the International Standards Organization. For the strength requirements, we needed a factor of safety of 1.5. As I mentioned in the previous slide, it has to withstand a load of 150 pounds. And of course, it has to be economically feasible. Of course, you could design something that won't fail under particularly any circumstance. You want to design the best, but still it must be economically feasible as far as materials, processing, and such. Here are the safety concerns we wanted to address. Of course, as I mentioned earlier, tip over is the main thing we don't want to do, or frame deformation or frame fracture, because that's the main safety with the children. We wanted to make sure you can do a quick extraction from the chair in case of an emergency, such as there's a fire or anything where the kids really need to be removed from the building. We didn't want to do it so that you had to roll the child out, because let's say a beam falls and blocks a doorway, so you can't roll it out of there. So we wanted to design it so that the kid could be quickly extracted and carried to safety. We also made it waterproof, so we could clean it to prevent any illnesses from occupant to occupant. So a quick wipe of household cleanser, something antibacterial, won't damage the material and will be able to sterilize it. We also wanted to avoid sharp corners and pinch points, because obviously that would make it very uncomfortable for the children. Plus, if they're hurt by the chair once, they would be less inclined to get into it again, of course. Who wants to be hurt more than once? So we also had to make sure that the brakes were capable. We didn't want to put the brakes on and then from friction slide off, or for the brakes to fail, to make sure it stayed on the slope. Here is our project architecture. As you can see, the top has the seat, which is composed of a back, headrest, armrest, and a saddle-like shape. We originally made a modular headrest, but we ended up finding and buying a chair that had the head support built into the back, which didn't sacrifice any functions that we needed. You can see that this green member right here is the tilt adjustment. It's a member that lengthens and contracts. This is connected to the bottom of the seat and to the gear in the back, which will turn it. So you turn the gear, the rod extends and contracts, and that affects the tilt of the seat. The handle for that adjustment is connected to the collar, which is the main function, one of the main components of the height adjustment. The collar sits on a screw right here, which is mounted to the frame via retainer bolt right there, and there are two bearings, to really make that a smooth motion. There's not much rubbing or wear. At the bottom of the screw is a chain drive, which is connected to another, which is two gears connected by a train that goes to this shaft right here. You turn the handle, which turns this gear to this gear, turns the screw, and then the collar goes up and down, raises and lowers. Everything, of course, is connected to the frame, which is supported by 4 wheels. 2 of the wheels will have the braking function. The frame is one of the most important components, because if it fractures and breaks, obviously that's mostly a safety concern. But if it breaks, it also renders all other options unusable. So that's the main concern. We also have foot supports right here that connect to the bottom of the chair. These are for adjustments for different size children, for different length shins, as I mentioned earlier, for children 8 to 12, and kids tend to vary at that age. And we also have a modular chest support, which comes out. Like I said, this is to remove so you can put the child into the chair, or in quick extraction, you just pull it out and they can get them out. If that was permanently mounted, you would have to put the child's leg over at the side, and of course that would be a lot more difficult than just setting them into the chair. So we want to make sure that this chest support could come out so that, as I said, easily put in or for a quick extraction.
I'm Will Waskell. I'm going to cover the design revisions as well as manufacturing of the chair. The first major design revision we had since last semester was that initially we had 4 caster wheels with independent brakes, and the panel brought up the fact that if the brakes weren't applied simultaneously, it would rotate. So in order to get around that problem, what we did is we replaced the rear casters with fixed wheels, and then we connected them via a pipe so that they both engage and disengage simultaneously. And then we did some testing to verify that that was enough. And the main thing was we couldn't go with force swivel just because it would be a very complex braking mechanism, and we thought it was just not going to be very feasible in the time we had. Our next modification was initially the height adjustment. The point of support for it varied with height as you adjusted it up and down. So we went and we removed it from the collar and we supported it by the frame so that it's a fixed position. It was a pretty simple fix. And initially we planned on having a 5-point harness. And after meeting with McMain's staff, they brought up some concerns about this. So we replaced that with a chest support and just a lap belt or seat belt, that holds their waist in position. And we also initially had a spring to help assist and equalize the force of bringing it up and bringing it down when you're adjusting the height. And just due to budget constraints, and it really wasn't a critical part, we completely eliminated the spring from the design. Our final revision was for the frame. Initially, we were planning on just having a straight tube come out here, but after meeting with the McMain staff, they expressed some concerns that the table height would be higher than a typical table to use with a chair, so we wanted to minimize the rod height of the frame. In order to do that, we just cut the frame tube shorter and then loaded plate metal here, which lowered the rod height. And it makes it somewhat more stable of a platform as well. Now I'm going to cover the manufacturing. The first component is our chest support. And for this, we utilized an existing component that McMain's had provided us with, and they just had it covered in marine vinyl, which is a waterproof substance, and that was the extent of the manufacturing. For our seat, it was one of the critical parts. It was the purpose of the chair, so we spent, in between the semester, we manufactured several seats of varying widths and varying shapes. And then at the beginning of the semester, we went to McMain's and tested these to see which one fit best, because we had a hard time quantifying the desired or the optimum seat shape. And how we constructed them was just to get rebond foam, which comes in 3/4 inch sheets, and then adhere that and laminate it to thicker and thicker heights until we got what we needed. And then we used an air grinder to machine the surface of it to remove foam. And we used paper templates to make sure that it was still symmetrical on both sides. And then once again, we covered that in marine vinyl as well. For our seat back, we wanted to get this part as cheaply as possible, and we couldn't deem manufacturing this ourselves when we could purchase one for so cheap. And we found a seat that had both independent armrests that rotate 90 degrees, which is one of our requirements. And like Justin said, we sacrificed the removable headrest, but we got this seat for cheaper than we could have manufactured, and then we just had it covered in the marine vinyl. For our seat base construction, we manufactured this out of mild steel 1/4 inch plate, and we used a water jet to cut out all the components, and then we had those components welded together and then had it powder coated. For the collar, we used 4130 4130 steel alloy for the circular parts, and it was just it was solid round tube, and then we machined the inner diameters. The front one is machined for a 2-inch Acme screw, and the rear one, we put a bushing in there to limit the friction on the bar that it slides on right there, a brass bushing, and that was the extent of the machining with that done on the lathe. And then we cut the flat plate pieces on the water jet. For our retainer, once again, we used a solid piece of round bar stock of tool steel, and we machined the inside to fit the jack screw as well as the bearings and the races, and then we put a race at the top to seal grease in, and we also have a horizontal channel here that feeds the grease to it, and the end of that is machined for a grease cert. Our jack screw was one of the more difficult components that we manufactured, and it was from 4130 alloy, and once again, solid bar stock, 2.5 inch diameter. We used a lathe to get the threads and the inner and outer diameters that we needed, as well as the bearing surfaces for the bearings located here. And then we drilled a hole in the base of it for a bolt that will attach our gear at the base. Our frame manufacturing was pretty complicated as well. Once again, 4130 alloy steel. We used a water jet to cut out the flat plate pieces, and then for